Okay, so our goal will be to develop a theory of integration, a general theory of integration. Um, and to do that, we will start by talking about sigma algebras, which is going to kind of give us a way to define measures on um, on spaces. We define measure spaces and define measures, which we can then further develop to um, talk about integration. So to begin, we will talk about what an algebra is. So an algebra of sets. So we say that an algebra of sets. So the definition we have, an algebra of sets on a set X is a non-empty collection. The non-empty collection, we call it A, or I want to draw a script A, non-empty collection A of subsets of X that is closed under finite unions and complements. So what I mean by that is when we say finite unions, we simply mean that if we have a collection E sub I from I equals 1 to n, so we have some collection of subsets of X where E sub I is a subset of X, then the union over n or over I, then the union from I equals 1 to n of E sub I is in A. And by closed under complements, we simply mean that if E is in A, then E complement is in A. So this is an algebra of sets, and we have some simple examples of an algebra of sets. Two of the simplest algebras of sets we can have are if we take the collection A, if we take the collection A to be equal to the set containing the empty set and all of X. So this is kind of like a trivial algebra, or well, there's two that are trivial. This is one of them. So we see that, of course, the union, so the union of any elements in A in this case, that's going to be an element of A again. And the complement of any element in A, so the complement of the empty set is X, and the complement of X is the empty set. So that satisfies the definition of an algebra. Um, the other standard trivial example is if we take A to be equal to the power set of X, right? So this is the collection, the set of all subsets of X. And this is also a trivial case because we see that the union of any subsets of X is again a subset of X, so it has to live inside of the power set. And we also have that the complement of any subset of X is again a subset of X, so it has to also live in the power set. So these are simple examples of algebras of sets that we can make. Um, just as in parallel to when we talk about topologies on sets, these two are kind of the um, the largest and smallest topologies that we can make on a set. Um, but for our purposes, what we really want is a sigma algebra, right? And sigma algebra comes from kind of strengthening one of our conditions here. So a sigma algebra. So what is that? So we strengthen one of our conditions. In a sigma algebra, we require that um, A is an algebra, or we'll call it M in this case. Um, so we have the same conditions as we started with before. So we let X be a set. M, that's terrible. M, a non-empty collection of subsets of X. So we have the same setup as before, but this time we require M to be an algebra that's closed under countable unions. So what this means is that if we have a collection, so we have a collection E sub I from I equals 1 to infinity, right? So this is a countable collection. So this is indexed, these are subsets of X that are indexed by the natural numbers. We could have repeats in there, we could have, any number of things go on, but as long as there's a countable collection, we require that. So if this is a subset of M, then the union from I equals 1 to infinity of E sub I is in M. Right, so this is a strengthening of the condition. So we require us to be an algebra. So M is an algebra, but it also has to be closed under countable unions. And by being closed under countable unions, we are automatically closed under finite unions, of course, because that finite unions are also countable unions. And again, our two examples up here. So our two examples over here, they still work and they are still sigma algebras. Clearly the first example, countable unions of any elements of A, so that the empty set or X are again, of course, elements of A. And in the second example, we have countable unions of any subsets of X. Well, that's, of course, going to be a subset of X again. So it's in the power set. So these are kind of some trivial examples. And what we want to do is we can kind of, we can point out that we're not only closed under countable unions, that we are not only closed under countable unions, but by the fact that we're closed under complements too, also tells us that we're closed under countable intersections, right? So this is kind of like a little claim here, right? If we have E sub I is a countable collection of elements, a countable collection of elements of M. That's terrible. I'm never going to get used to writing this. Then the intersection from I equals 1 to infinity of E sub I is in M. Now, how do we see that? Well, what can we do? Well, what we know is that if we have this countable collection and we look at the union, right? We know that the union of E sub I complement, right? We know that each E sub I complement is in M, right? So the arbitrary union of these guys, this is in M, right? Because M is closed under countable unions. But since this is in M, we also know that its complement is also in M, right? So this implies that the union of E sub I complement, and we take the complement of that whole element, this is again going to be in M. But by De Morgan's laws, right, this implies that the intersection of E sub I complement is in M. But of course, that's just equal to the intersection of E sub I, and that's in M. So we see we have some nice properties of sigma algebras. So sigma algebras are closed under countable unions, they're closed under countable intersections, and they're closed under complements. Now, these sigma algebras are kind of unruly, and just like with a topology, um, we want something to describe our sigma algebras in a more um, a way that we can wrap our hands around a little bit. Now, unlike a topology, where when we have a topology on a set, we need to have um, you know the definition of a topology is that the whole set and the empty set are elements of the topology, arbitrary unions and countable intersections are elements. So those operations are kind of easier to have a handle on, and it's easier to generate other elements through those operations. The issue that we run into with sigma algebras is the complements, right? So when we look at the complements of sets, we kind of mess up the nice properties that we can get, when we get a basis for a topology. But with that being said, there are some nice we do have some control over our sigma algebra, um, and that's going to be in the following proposition. So this proposition is important, right? So if X is a set, and let's say we have a collection of sigma algebras, or we'll call them M sub I, or actually, since we're not going to be indexing these by M sub alpha, right? So X is a set M sub alpha. So this is a collection of sigma algebras. So we have a collection of sigma algebras on X. Then the intersection is a sigma algebra on X. Okay, so this is an important small proposition because this will allow us to define what it means for a sigma algebra to be generated by a set. And the proof of this is pretty standard, right? So this is kind of a standard proof to show that the intersection of a collection of some objects satisfies a certain condition. So what do we want? Well, we want a collection E sub I, right? So we want countable unions, and we want complements, right? So we have a collection. So we have a collection of subsets of the intersection of our sigma algebras, right? Well, then we know that E sub I is in M sub alpha for every alpha in J, right? Because J is our indexing set. And for all I in N, right? So each element, each one of our subsets, E sub I, is in each alpha, M sub alpha, for every alpha and every I. Right, and what does this tell us? Well, this tells us that the since every E sub alpha is in M sub alpha, that tells us that the union over I of E sub I is in m sub alpha. So this is from I equals 1 to infinity, right, for every alpha in J. But of course, this just tells us that the union of E sub I, that's going to be in our intersection of M sub alpha. Okay, so that's good. So we have countable unions, which also implies countable intersections. Now we just need complements. Actually, it doesn't imply countable intersections because we need complements for countable intersections. So complements follow suit the same way. So if E is in the intersection of M alpha, then E is in M alpha for all alpha in J, right? That implies that E complement is in M alpha for all alpha in J, which of course implies that E is complement is in the intersection for all M alpha, or in the intersection of M alpha over alpha in J. So that's good. So we have the intersection of an arbitrary family of sigma algebras is a sigma algebra. Now, what we can do is we can define a sigma algebra generated by a set. Okay, so this is going to be a definition. So we're going to have X as a set, and we're going to take E is a subset of the power set of X. Okay, so now X is a set. E is a collection of subsets of X. So this is just a collection of subsets. Right, so E is just a collection of subsets of X, non-empty collection of subsets of X. So we're going to define M of E, the script A. So we're going to define M of E to be the smallest sigma algebra containing E. And now, by definition, right, we have that M of E is equal to the intersection over alpha in J of M sub alpha, right, where E is a subset of M sub alpha for all alpha in J, and these are sigma algebras. So this is called the sigma algebra generated by E. Okay, so what are we doing is we're taking a collection of subsets of X, and we're looking at the sigma algebra, the smallest sigma algebra that contains it. And how do we obtain the smallest sigma algebra that contains it? Well, we look at all sigma algebras that contain it and then take their intersection. Intersecting all of those sigma algebras gives us a sigma algebra like we proved up here, and that will contain E and be the smallest sigma algebra that contains E. Now, there's not much that we can say apart from that this is the smallest sigma algebra containing E. When we compare that to something like, well, something very, very constructive, like a basis for a vector space, where we can write each element of the vector space as a, if it's a finite dimensional vector space, as a finite linear combination of elements of the basis, or in a topology, when we have some nice theorems about if we have a topological space with a basis, then every open set can be written as the union of basis elements. There's not much that we can say when it comes to sigma algebras, because of the issue with taking complements and things like that. One thing that we can say, though, is that, which is which is going to be useful, right? So if E is a subset of the sigma algebra generated by F, right? So here, so we'll say this. So E and F are subsets of the power set of X, right? So these are just collections of subsets of X. And if E is contained in the sigma algebra generated by F, then the sigma algebra generated by E is contained in the sigma algebra generated by F. So this is kind of like the strongest that we could say. This is one of the strongest statements that we can say about the constructivity of sigma algebras. So if our sigma algebra contains some given subset of the power set, then the sigma algebra generated by that is contained in the sigma algebra generated by F. So this is pretty simple, right? And this basically follows from definitions, because if E is contained in M of F, then by definition it's one of these M sub alphas, right? So it's going to be one of these M sub alphas. And we know that M of E is equal to the intersection of all of these M sub alphas, right? So that implies that M of E has to be contained within M of F, because of our condition up here that M of E is contained is the intersection of all sigma algebras containing E, and this M of F is a sigma algebra that contains E. So M of E must be contained within M of F. Now, so we've generated sigma algebras, and there are some special sigma algebras that are going to be used later on. There's one special one in particular, so when we talk about sigma algebras, like I said, one of the most important sigma algebras are is the Borel sigma algebra, right? So that's what we're going to talk about now, um, the Borel sigma algebra. So this comes from if we have a metric space, so let X be a metric space, or more generally, a topological space. What we do is we take the sigma algebra generated by all the open sets. So take, we call it B, right? So we'll say B sub X to be the sigma algebra generated by the open sets. Now we have just to keep in mind where the sigma algebra is being generated. So just to reiterate, we have our set X, and we have our power set of X. Right now, all of our sigma algebras live inside of here. So all of our sigma algebras live inside of here, of the power set of X. What we do is, inside of the power set of X, which is a massive object, if X is R, let's say, or q or anything crazy, the power set of x is going to be massive. So all of our sigma algebras are contained within the power set, and what we do is we look at the sigma algebras that contain all of our open sets, right? So we look at sigma algebras that contain all of our open sets, and every sigma algebra that contains every single one of our open sets, we intersect them, and we get the sigma algebra generated by the open sets. And we say that an element in Bx is a Borel set. Now again, the sigma algebras are unruly. There's no nice way to talk about them. There's no nice way to describe really what we have. But so but we can kind of get an intuition for what we have here. So since a sigma algebra contains all countable unions, countable intersections, and complements, the Borel sigma algebra contains all of our open sets. It contains all of our closed sets, right? Uh, so we have in particular Bx contains all of our open sets, all of our closed sets, right? Because if it contains all of our open sets by definition, right? So this is by definition, and it contains all of our closed sets since um, the complement of a open set is a closed set, so it'll contain all of our closed sets, right? So that's from complements, and it's going to contain all countable unions and countable intersections of our opens and closed sets. So we're going to get sets that are not open or closed. We're going to get some kind of, some different types of sets that are not open or closed. We're going to get stuff in the middle. And there are a number of ways that we can look at our Borel sigma algebra. So let's say we're just looking at R. So we're going to let X be equal to R. So we're going to let X be equal to R. Then the Borel sigma algebra, so this is B sub R, can be generated by each of the following. So we have a couple of generating sets for our sigma algebra. So the first one is E1, which is just going to be the set of all open intervals. Right, so this is the standard generating set for the Borel sigma algebra. That's the one we defined before. That is the definition of taking the Borel sigma algebra. The second one that we can have are all closed intervals. The third generating set that we can take are half open intervals. So this is going to be E3, which is going to be AB. I'm going to stop writing A less than B because it's obvious. E4, which is going to be equal to the open on the left, closed on the right. Then we could also have open rays. So E5. E6 is going to be negative infinity to B. Right, and the last generating set that we can have for the Borel sigma algebra are going to be the closed rays. So these are all possible generating sets. So what are we saying here is that, well, our standard generating set, which is this one. So if we look at the power set of R, and we look at all sigma algebras in the power set of R containing E1, right, or containing all of our open sets, then we'll get the Borel sigma algebra. If we look at, let's say, we look at the power set of R, and we look at all sigma algebras containing all of our closed sets, we'll get the same sigma algebra that we got in case 1. And similarly, if we look at all the other cases too. So the sigma algebra generated by any one of these collections of sets is going to give us the same sigma algebra, the same Borel sigma algebra. Right, and the key item here that we're going to use is our lemma before, that if E is contained in sigma algebra generated by a set F, that implies that M of E is contained in M of F. So this is going to be the key, this is the key theorem here that we're going to use, because as we said before, the sigma algebras are unruly. This is kind of the only control that we have over them. So what we're going to do is we're going to look at these containments, and we're going to use some facts about R, right? So every open subset of R under the standard topology can be written as a countable union of disjoint intervals. Yeah, and is that correct? So let's prove some of these, right? So what do we know? Well, we know that the Borel sigma algebra on R, that's going to be equal to the sigma algebra generated by the open sets. I made a mistake before because this isn't our standard definition. This is kind of like a subset of our standard definition, right? So open sets can also be kind of unruly too, but we can tame them a little bit by just taking our open intervals. I said before that this was our standard definition, which it's not. The sigma algebra generated by E1 is not the it is the Borel sigma algebra, but it's not obvious that it's the Borel sigma algebra. So what do we know? Well, we know that E1 is contained in BR, right? Since E1 is a collection of open sets, and BR is generated by all open sets. Okay, so that's good. So we know we have that. So this implies that we have the sigma algebra generated by E1 is contained within the Borel sigma algebra. Now we have to go in the opposite direction too. we have to go in the direction so we need to show that the Borel sigma algebra is contained within the sigma algebra generated by E1, right? But if let's say we let K be the collection of all open sets in R, right? So K is going to be the collection of all open sets in R. Well, we could see that K is actually contained within M of E1. Right, now why is that? Well, as we noted before, if U is open, then it can be written as a countable union of disjoint intervals that I kind of hand-waved before. The proof isn't too bad of that. So it can be written as the countable union of disjoint intervals, but we know that that M of E1 is generated by the open intervals. So this implies that K is a subset of E1. Right, since every open set is a union of disjoint open intervals, we see that we have this containment. But that implies that the Borel sigma algebra on R is a subset of M of E1 by the lemma. So then we conclude that the Borel sigma algebra on R is equal to the sigma algebra generated by E1. So this is good. So we've boiled down our Borel sigma algebra, right? So we have this crazy sigma algebra generated by all open sets. We boiled it down to just looking at open intervals, which is good. We have a handle on it. And there are so the proofs of the other situations are similar. So for the second one, right? Um, so for the second one, right? So E2 is equal to the collection of closed intervals, right? Well, right off the bat, we know that E2 is a subset of the Borel sigma algebra. Why? Well, because we know that the Borel sigma algebra is generated by all open sets and therefore contains all closed sets as well as being complements of open sets. So this implies that M of E2 is contained within the Borel sigma algebra. Um, now, we want so just to look at what that looks like, right? So if we have a closed interval AB, how can we write that as the complement of an open interval? Well, we can look at this is actually going to be equal to the interval negative infinity to A union B to infinity complement, right? So we know that these two guys are in the Borel sigma algebra, which is good, and we know that their complement will be AB, the closed interval. So this does show that E2 is contained within the Borel sigma algebra. Now we want to show that the Borel sigma algebra on R, we want to show that this is actually contained within the sigma algebra generated by E2. But from our previous work, since the Borel sigma algebra on R is generated by E1, we can show that E1 is contained within the sigma algebra generated by E2. But actually, this is quite simple to note, right? If we have an open interval, right? So if we have an open interval, oops, we have that. So we can kind of create this open interval by intersections of closed intervals, right? So we can kind of look at this as the intersection from n equals 1 to infinity of a minus 1 over n to b plus 1 over n. So we're kind of converging on AB from the outside. And this is a countable intersection of closed intervals, which is of course contained within M of E2. So this implies that E1 is contained within M of E2, which implies that the Borel sigma algebra on R is contained within the sigma algebra generated by E2. So these are the first two. So we've done this one and this one. I'll come back and we'll do the next couple of them. So E3, E4, E5, E6, E7, E8. We'll do that in another video where we go over the exercises of this section. So this is a good place to stop. There's other things that we can talk about, like the product sigma algebra, but we won't go into that until we get to the product measures. When we talk about product measures and the Fubini-Tonelli theorem, we'll come back to this and we'll go over product sigma algebras.